In this segment, we will discuss the likelihood and impact of events, and mainly the relationship between the likelihood and the impact. The discussion will be based on the so-called power law, something that you have seen before in this class. And throughout this segment, I will use an example of earthquake and look at the frequency and impact of earthquakes. So let's start with the first example. And here we see a screenshot from the US Geological Survey Earthquake Hazard Program. This is a depiction of earthquakes of magnitude 5.0 or higher that actually took place from 1900 to 2016. As you can see, there are lots of earthquakes in the Pacific coast of the United States, right here, and also here in the Pacific coast of Mexico. There are some in the northwest United States, right here, and little more inland, and then sporadic earthquake throughout the United States. We can conclude from just looking at the map that there's a higher likelihood of earthquake if you live along the Pacific coast of the United States and Mexico. So let's look at some data. This data is different. The source of the data is different. It's just from Southern California, and it's the data from 1987 to 1996 of earthquakes. Again, it is taken from the US Geological Survey. And in this table, we see the magnitude measured along the Richter scale and the count per range. So for example, we had the 912 earthquake of between 3.5 to 3.9 on the Richter scale. And we had the 9,471 between 2.5 and 2.9 on the Richter scale. So, and very few, for example, only 32 between 5 and 5.4. We can also look at how many earthquakes above the lower bound of M. So, for example, we had in these years 13,590 earthquakes above 2.5, the lower bound of M, the magnitude. There were 423 earthquakes of magnitude 4 or higher between 87 and 96. You see, there were 423 4 or higher. So we can plot this cumulative total along the axis of M versus the magnitude, the number greater than M. And we get something like this. This is a typical graph. It shows that there are a large number, as we show from the table, of 2.5 or higher. There are a smaller number of magnitude 3 or higher. There are even smaller number of magnitude 4 or higher. And the number goes down as the magnitude goes up. We can simply calculate the percentage or fraction of earthquakes larger than the lower M in the range. This is shown on the right-hand side column of the table in front of you. So for example, the top cell on the right-hand side column shown the number 100. 100% of the earthquake are larger than 2.5 magnitude. We can also look at it in terms of a graph. This is similar to the graph that we had before, but instead of numbers, we see percentages. And again, we can make similar statement. For example, if we want to see how many earthquake would be larger than magnitude 3, it shows that about 30% of the earthquake are larger than 3. The same thing can be seen from the table. We see that the second number on the right-hand side column is about 30%. So 30% of the earthquake are larger than magnitude 3.0. Assuming, of course, that there's no change in the forces that causes earthquakes, we can interpret this as the probability of an earthquake larger than 3 in the next 10 years. Again, assuming that there's no fundamental change in the physics. What we do is the following. We plot the logarithm. You see, this is the logarithm of the number greater than m, and this is m. Now, to get the equation of the curve, what we need is, we can base it on this 2.5 and extend the curve and see where it will meet the m-axis at 0. So we try to find this point. This is the calculation. We go from 2.5 at a slope of 0.98. We add the 413, this number, and we get 658. So the equation of this line is y equals 6.58, y equals 6.58 minus 0.98 times m, close to 1, the slope. So this is what we had before. This, you can get exactly these numbers from this table. So now we want to develop the actual model. So let's first plot the original curve just from the data. And remember that the equation y equals 6.58 minus 0.98 times m, in that equation y is actually the logarithm basis 10 of the number greater than m. We want to take the exponent of both sides. The exponent of the log is just the number, and the right hand side become an exponent. So here we have the right hand side will become 6.58 minus 0.98 times m. This is the equation that we got. Y, or cumulative number greater than m, the number greater than m is 10 raised to the 6.58 minus 0.98 times m. So this is basically the Gutenberg-Richter law. The number of events with magnitude greater than or equal to m is 10 raised to the power of a minus b, some general a and b constant. In this equation, a is somewhat less important, it is a scaling constant. B is the important constant because it is related to the magnitude. B is what is related to the magnitude. That's the important constant here. So now let's plot this model. Let's plot this equation and see if it fits the observation. And if we plot it, you see that the new curve comes right on top of the observation. So this is the model. The model is given by this curve, and it fits the observation very nicely. We conclude from this that we have a good fit. Now, sometimes you will see the data plotted differently in this type of power laws. You will see, instead of the total above, you see the cumulative total below the top m in the plot. So instead of the total greater than the lower m, you'll see the total less than the higher m. So here, what do we have here? We have 9,471 less than 2.9. And we have 13,590 less than 7.4. And we can of course also calculate the fractions here. And if you do it, if you plot it, plot the fraction. You can plot, of course, also the numbers. In this case, I plotted the fraction against the higher m in the range, because we are plotting the total less than the higher m, and in this case we get something like this. In many power law discussion you've seen a curve like this.